This lesson, you're going to get a quick overview of magnetic fields. We've now covered everything we need to know for the moment about things to do with the electric force. So let's take a moment to revise what we know. Firstly, electric charge. It's measured in coulombs, and it's always a multiple of one basic unit of charge, which we label E, and it's the charge on an electron, approximately minus 1.6 by 10 to the minus 19 coulombs. Then the Coulomb force is the electrostatic force between any two objects with charge. It is proportional to the product of the two charges and inversely proportional to the square of the distance between them. The electrostatic force happens because all charged particles have an electric field around them. Remember that a field is an area where something experiences a force. The strength of an electric field is measured by the force on a test charge, and so it is given by E equals F over Q naught. If we have a number of point charges or a distributed charge, we have to add up the field due to each point. For distributed charges, you will remember this means integration. We looked at a few examples of this, and then we saw an easier way. Gauss's law says that the total amount of electric flux coming out of any Gaussian surface times E naught, which is the permittivity of free space, equals the charge inside the surface. Remember that the electric flux through any area is equal to the electric field E times the surface area. From there, we move to electrical potential energy a distance away from a point charge, which is defined as the work done to move a test charge from the point to infinity. Remember that a charge moving in the direction of the force on it is losing potential energy, while a charge being pushed in the opposite direction to the force on it is gaining electrical potential energy. From that, the electrical potential is the potential energy per unit of charge. The potential difference is what we are usually interested in. That is the difference between the absolute potential at two different points. For a uniform field that we most often deal with, the potential difference V between 2 points is the field strength E times the distance delta x between the 2 points. Electrical current is defined as a flow of charge. The current passing through a surface is the charge per unit of time passing through. Once we have a potential difference, or voltage, across an object and the current passing through it, we can find the object's resistance using Ohm's law. Finally, the electrical power of a device is its rate of converting energy. Since energy U is Q times V, and power is energy over time, that means power equals delta Q over T times V, and that means hence power equals current times voltage. Before we move on to magnetic fields, let's check your recall of electricity.